All right, so continuing now to the mesh module, where I'm going to define the mesh associated with this particular model. Once again, we're back to the mesh module and we're going to seed the part first. And press the seed window and it's going to ask me the same familiar question from before. Should I seed it with 18 inches? Approximate global size of 18 inches, I will change that to 12. And that's done. And it says global seeds have been defined. You can see the seeds. Now, before I generate the mesh, I'm going to associate this with a particular element type. So let me do that. I'm going to click that icon that reads S4R, and I'll assign some element types to this structure. That's the structure to which I need to assign element type. And it has become extremely slow because I'm trying to upload the first video while I make this second video. And it's become extremely slow. Okay, so it's a standard element. It's a beam element. It already understood the family that we need to be located in. There are different families of elements, but we don't need to mess around with that because it's already selected the beam element. And there are two options here. I can go with a hybrid formulation, or I can go with a cubic formulation, or I can go with a shear flexible formulation. It tells me that it's element B21, which is a 2-node linear beam in a plane element. And I'm going to keep the shear flexible option. There is a reason for that. And the reason is that if I keep the shear flexible option, then it will show me the shear force diagrams as well. If I keep the cubic formulation, which means that shear deformations are ignored, in that case, it doesn't give me the shear force diagram. It says, well, you ignored the shear deformation, so you clearly don't need to know how much shear force there is. So instead of using the cubic formulation, I'll keep the shear flexible, and that will allow me to use a Timoshenko beam element. Although I know that the shear deformations are really not going to be significant, I'm keeping the shear flexible element so I can generate the shear force diagram along with the axial force and bending moment diagrams. So I kept the shear flexible element. We're working with element B21. And now that we're done assigning the element types, we can generate the mesh. In order to generate the mesh, I'll just be clicking this icon. As soon as I get control back of the screen, it has become extremely slow because it's trying to upload the first video while making this second video. I see that's the uploading going on. I wish there was a way to pause it. Not anymore. It's already started uploading, so Okay, that key should generate the mesh. It should ask me, is it okay to mesh the part instance? My answer is yes. And it should go ahead and generate the mesh. All right, that's pretty much the finite element model. We've defined the loads, the boundary conditions. We can we can check the elements. Sometimes, like last time I showed you how to do that. You can use the query tool to ask it, what is that particular element? When you click on the specific element, it'll tell me what element type it is. And there it is retrieving that information, and it's showing me below that this is a linear element of the type B21, which is shear flexible, which is what I assigned. So I'm making sure that the mesh that has been generated according to my instructions, which is always a good idea. So that's the query tool. Used more often in post-processing, but sometimes you can use it in pre-processing as well. That's it then. With the completion of the mesh module, I'm just going to create a job and submit it, and then we'll be ready to move on to the post-processing. And even in the post-processing, there's just one thing I need to show you about the frame element, and then you'll be on your way to doing your homework and so on. So here I'm going to switch over to the job module. It's still going very slowly. There we go. It's in the job module. At this point, I should create a job and submit it. CE592, homework 1-2 for students. It's a standard analysis. And now that the analysis has been created, I'll hit the submit button. And that will submit the job. At which point I can monitor its progress. It's telling me that the job finished even before I could open the window. That's how quickly the job ran. Okay, it was the simplest model in the world. It should be pretty quick. At which point now I can click this button for results and start post-processing the results from this finite element analysis. And the main difference that I wanted to talk to you in this post-processing is that in order to plot the shear force and bending moment and axial force diagrams, you have to plot the variables SF1, SF2, and SM, where SM represents section moments, SF represents section forces. So you'll have to just scroll down till you come to SF. There you see, that is SF. I don't know if it took the click or not. There is SF. And it has the options of plotting SF1 and SF2, both of them. Now, the problem is it's a contour plot. And what do you do with a contour plot? It's really hard to, because I really wanted an axial force diagram for SF1. So in order to generate the axial force diagram, all you need to do is look at the contour options. And this was something that Abaqus added after 30 years of civil engineers complaining that I can't plot a bending moment diagram. So they finally added this option where you can have a contour type called line. You can say show tick marks for line elements, and you can click the button apply. And now instead of plotting a contour element, making a contour plot, it's making a line plot where the gradation here is the contour and you're looking at the axial force diagram. But it's plotting it on the deformed shape, and we are traditionally used to looking at it on the undeformed shape. So all you need to do is click that button again and hold it down till it shows you the option to plot it on the undeformed shape. And there we go. What was I expecting for the axial force diagram? I was expecting the axial force in the columns to be somewhere about 250, and you're seeing the axial force diagram associated with the two columns has been reported here. And of course, there's additional axial forces due to the overturning moment that has added to one side and subtracted from the other side. So you can look at SF1 as an axial force diagram. You can also look at SF2. I wonder what SF2 will look like. And there it's plotting me my shear force diagram associated with this analysis. All right. And I can also, of course, plot the bending moment diagram, which will be coming from SM. There we go. There's your familiar bending moment diagram associated with the problem that we are looking at. Fixed base, lateral loading, and gravity loading being applied. You're looking at that double curvature bending moment diagram that you expect to see. And of course, you can always reduce the number of contours, as I mentioned before. Instead of having 12 tick marks, you can reduce it down to 6. And if you didn't want to see the tick marks, you could switch them off. And maybe you don't want to do that. And there's the bending moment diagram. So those were some of the new things that you haven't seen before with this. Of course, you can reduce or increase the number of contours in this plot and look at your axial force and shear force diagram. Of course, you can also look at your reactions, same way as before. You can go on to symbol. And then in symbol, you can plot, you can make a vector plot of your, first of all, it's trying to show you the direction of SM1, which is very useful. If you wanted to look at the direction of SM1, it's providing you with what that direction is going to be. SM1 is producing stresses in the direction shown of the arrows. I can look at reaction forces. And you can see the two resultants at the bottom. You can also look at RF1 individually. It's coming through. RF1 will be the reaction forces. Let's see. There we go. They are equal to about 31, adding it up to be about 60. And then you've got RF2, which is your reaction force in the direction, the vertical direction. There's your reaction force 2, showing you the reaction at the bottom. Once again, you're looking at that. And of course, you can pick out the values using the probe values tool, which I showed you earlier. You can save the results. You can make different plots, and of course you can look at the individual stresses in the different beam elements as well. So for example, you can look at the stresses, although you probably don't want to look at it by symbol. Just looking at the stresses. There's a variety of post-processing you can perform. Just struggling with the speed here because I'm trying to save the file. I shouldn't have done that. It's making everything really slow. Looking at the stresses here, and of course you want to look at S11. And of course you can also look at the options for looking at the different invariants and so on. There's looking at S11, and it's showing me the values of the stresses. Now, when I get to looking at the values of the stresses, I have the option of, let me talk about this a little bit. So stresses are being shown in the beam element, but stresses where are we talking about? And so in order to understand that, you need to go back to the result field output key, and when you do that, you will see the location section points. And these section points, you can specify the section point at the bottom. Remember when I was creating the output module, I showed you have the option of creating or saving the results at different locations of the section. We went with default values, which means that it gives us the locations at the bottom, the top. It also gives us the envelope of the two as shown here. So you can pick any one section and you can look at the stresses either on the bottom or on the top. And of course, you have to figure out how you're using the results and so on.